This video is a review of circular motion and gravitation for AP Physics 1. When we started studying circular motion, we talked about something called uniform circular motion. And the circular motion is uniform if it's traveling in a circle that has a constant radius r with a constant speed v. And so I've got a picture of this to the right. And if you imagine the thing traveling with a speed v, so I have vi and vf shown as two different instances of a speed v, and the distance to travel around that circle is the circumference of the circle, 2 pi r, where r is the radius of the circle. And if it takes an amount of time, capital letter T, for it to move in that circle, then we could write the following equation, right? The speed, radius of the circle, and the amount of time to go around that circle are related by that equation. And so we could calculate the amount of time it takes for an object to move around in a circle as 2 pi r divided by the speed of that object. And that's important because if an object is moving in a circle, there's some more information that we know about that we wouldn't necessarily know about if the object were accelerating in a different way or not moving in as regular a fashion. Also, we learned that, as drawn in my picture, if initially the velocity is pointing up and then a moment later in time the velocity is pointing a little bit to the left, maybe the speed of this object is constant. It moves around with a constant speed, but because the direction of the velocity is changing, initially it's pointing like this and then afterwards it's pointing like this, at every moment in time as the object moves around the circle, its velocity's direction is changing. And so because of that, the direction of the speed is changing, and if the velocity, either its magnitude or its direction, is changing, then that by definition means that the object is accelerating. And if the object is accelerating, then we should figure out what direction that acceleration points in, and we should figure out what is causing that acceleration. And of course we know that all accelerations are caused by forces, and so this led us to talking about what kinds of forces cause objects to move in a circle. So now looking a little bit closer at this uniform circular motion, we find that the velocity v is always tangent to the circle. So it always points perpendicular or tangent to the circle at every point. And the acceleration of the object as it goes around that circle would point in the same direction that the change in velocity points. And so our equation for acceleration in general is a equals delta v over delta t. And we know that the direction of the change in the velocity would be the same as the direction of the acceleration. And change in velocity is the same thing as v final minus v initial. And so if we could figure out what direction v final minus v initial, those two vectors in my picture, point, then we could figure out what direction the acceleration is in. And so first, all I did was I wrote down what the directions of vi and vf were. Vf points up and to the left like that, and vi points upwards. And so the vector that represents delta v would be vf minus vi, those two vectors subtracted. But I don't know how to subtract vectors. Instead, I know how to add vectors because we've used something called the tip-to-tail method to add vectors. So I'd much rather add vectors together than subtract them. And the way that I do that is just a little nuance, is to say that instead of doing vf minus vi, I'm going to do vf plus minus vi. And so if you notice, all I've done with vi is I've turned the vector upside down, and by flipping the vector like that, it now represents the negative of that initial velocity vector. But now it means that I can add those two vectors together to get the direction of delta v. And so I take vf, which still points up and to the left like this, and now add to that vi using the tip-to-tail method. So I place the tail of the minus vi vector onto the tip of the vf vector. And so now that points down like this. And the sum of those two vectors starts at the tail of vf and points toward the tip of minus vi. And so that vector minus that vector delta v is shown there in red. And if you look back up at the picture, then that shows pretty clearly that that delta v vector points toward the center of the circle. And so therefore the change in the velocity points towards the center of the circle, and so the acceleration, which points in the same direction as delta v, also points toward the center of the circle. Now, there are a lot of details here, but we really do need to remember this final point, that the acceleration, and therefore the force that causes the object to move in a circle, always points toward the center of the circle. Continuing on with this idea that the acceleration and therefore the force causing circular motion always points towards the center, we defined what we call a centripetal acceleration. And centripetal means center seeking, so that's an appropriate name for this because the acceleration and force always point toward the center. And we defined this equation which says that centripetal force, Fc, is equal to mass times centripetal acceleration. So it still looks like Newton's second law, and of course force is a vector and acceleration is a vector. And that centripetal acceleration has the form of v squared over r. And so centripetal acceleration is always equal to v squared over r, but more practically we often input that into Newton's second law in order to solve for something. And so the v squared over r represents the acceleration alone, and m times v squared over r represents the centripetal force. If I look at the units down below for centripetal acceleration, velocity has units of meters per second. In this equation it's velocity squared, and so that would be meters squared per second squared. And the distance from the center of the circle to the object, which is r, would be measured in meters. And so if one of those meters cancels, we get units of meters per second squared, and those are the units of acceleration. Additionally, we talked about the idea that centripetal force is never a new force. So when we talk about centripetal acceleration or an object moving in a circle, we do need to have a name for what we call this thing that pulls it towards the center, but it's never a new force. So if I'm swinging a ball around in a circle by a rope, then it's the tension from the rope that pulls the object toward the center. If there are clothes moving around in a washing machine, then it's the normal force from the walls of the washing machine that pull the clothes toward the center. If it's a roller coaster track where something's moving around in a loop, then maybe at the top of the loop, the weight of the cart points down, but also the normal force from the track points down. And so those two forces together are providing the centripetal acceleration. And as I said, for centripetal acceleration problems, we're very often going to be invoking Newton's second law, F equals ma, to solve problems. But we also need to remember that the a in that type of an equation where the object is moving in a circle needs to be replaced with not just some generic acceleration, but specifically a centripetal acceleration that's equal to v squared over r. And lastly, a point that I'd like to make, which is written in yellow on the right-hand side, is that if the centripetal force is removed, if we take it away, then the objects should fly off in a straight line. Because if I remove the centripetal force, then I've removed the centripetal acceleration, and so the object, if it has some constant straight line velocity, which for uniform circular motion it does, if I remove that force, then the object should move off in a straight line. And the example of this is if you're swinging a ball in a circle and somebody cuts the string, or if the string breaks, or if I just let go of the string, then we should expect that if we took a video of the resulting motion of the ball, that it should move off in a straight line. And that's consistent with Newton's laws, right? An object that is not subject to a net force will just continue to move off in a straight line. Here I have a couple of examples of how you might apply Newton's second law to a situation where something's moving in a circle. And on the left-hand side I have a little roller coaster track where it starts off at the top and it goes through this loop. And most importantly, at point C, the object is at the top of the loop, and so it is in part of the loop. And if the loop is a circle, then it's in uniform circular motion at that point in time. And so for that reason, we could use Newton's second law to say that the gravitational force, the weight of that cart, points downward, and the normal force from the track that pushes on the cart also points downward, because the normal force always points perpendicular to the surface. So both of those forces are pointing downward. And the center of the circle also is, relative to point C, downward. I think it's extremely important for you to always define and understand where is the center of the circle for a circular motion problem, because that is the direction that the acceleration will point in. And so in this case, I've defined positive y as pointing up relative to point C, and so at point C, the acceleration also points downward, and so in my equation, the acceleration should be put in as minus v squared over r. And maybe you remember doing some conservation of energy problems with roller coasters where eventually, if we wanted to understand the motion of the object while it's in the loop, we had to invoke Newton's second law and write this uniform circular motion equation. Similarly, on the right-hand side, I have a Ferris wheel where these carts are 90 degrees apart, and so at each position, what's happening with the force that would be holding up those carts from the axle and the weight of those carts maybe is a little bit different in each case. And you should think about what that looks like in each case, but I specifically want to look at point C. Point C is at the bottom of the Ferris wheel, and at that location, there must be an axle that's holding that cart onto the Ferris wheel, and that axle would exert an upwards force on that cart because the weight points downward at point C. So something has to be lifting it up. And here I want to pay particular attention not only to the directions of these forces, but also the magnitude of these forces. Because the object in this Ferris wheel is presumably moving at a constant speed at a constant radius away from the center, it's in uniform circular motion. Therefore, the net force exerted on this Ferris wheel cart must be pointed or directed toward the center of the circle. Therefore, I know that the force from the axle has to be greater than the weight. Not just equal to, but greater than the weight, because if an object is moving in circular motion, then a force has to point towards the center, and too often we study cases where there's only one force being exerted on the object, so it's very obvious that that force points towards the center. But here we have an obvious case, similar to the roller coaster, where there's definitely two forces acting on the object. And so while one of those does point towards the center of the circle, it's important that you realize that the net force is what has to point towards the center of the circle. And so in this case, I know for sure that the force from the axle has to be greater than the weight. And for that reason, in my equation, I would write F axle minus mg is equal to mv squared over r. The acceleration points towards the center of the circle, which is upwards and positive. mg points away from the center of the circle, so it's downwards and negative, and of course the force from the axle is upwards and positive. And if I were to solve this for the axle force, I would get mg plus mv squared over r, which hopefully helps illustrate that yes, the net force does point up because the force of the axle is bigger than that gravitational force. Lastly, I'd like to talk a little bit about gravitation as well. One of the main things that we studied when we studied gravitation was Newton's law of gravitation, which says that if I have two objects, mass 1 and mass 2, whose centers are separated by a distance r, so importantly, r represents the distance between the centers of the two objects, then there is a force of gravity that is exerted on both of those objects that is equal and opposite, that's given by Newton's law of gravitation. And while the force of gravity is proportional to the product of the masses and is inversely proportional to the square of the distance between those two objects, it's not equal to just that. There is a constant of proportionality. Okay, a constant that determines exactly what that force is, and that constant in the case of Newton's law of gravity is the universal gravitational constant, capital letter G, or big G, which is equal to 6.67 times 10 to the negative 11, so it's a very small number. And this is why, while gravity is always an attractive force, and gravity always exists between really any two objects, the fact that G is so small, it's a very small number, in order for the gravitational force to be like anything appreciable, the masses have to be very big, right? In order to overcome this constant, which has such a tiny value, one of those masses or both of those masses has to be very big in order to calculate some force of gravity that would be measurable. So between two people on the surface of Earth, two objects that are 70 kilograms maybe, the force of gravity is tiny. But between one of those people and the Earth, which has a much larger mass, the force of gravity is appreciable. And lastly, I'd like to reiterate that the force of gravity exerted on two objects, m1 and m2, is going to be the same regardless of whether they have the same mass or not. And this is something that's illustrated by Newton's third law. For every action, there's an equal and opposite reaction. Here, the action and reaction pairs of forces are the gravitational forces that each object exerts on one another. So even though I have very little mass and the Earth has a lot of mass, when the Earth pulls on me with a gravitational force, I pull on Earth with that same gravitational force, because that gravitational force is generated due to the mutual interaction of these two objects. Now, I happen to have not very much mass, and for that reason I accelerate towards Earth at 9.8 meters per second squared. The Earth has very much mass, and so for that reason it does not accelerate upwards at 9.8 meters per second squared. It accelerates upwards with some meaningless acceleration, and that's why when I jump up, the Earth doesn't really move, but I come flying down towards the Earth. Now we can look at a couple of the finer points of what we learned about gravitation, and that is, for example, at Earth's surface, we know that the force of gravity acting on me is also equal to my weight, right? Which is m times g. And so I have two expressions for the force of gravity, Newton's law of gravitation, but also my weight, as long as I'm at the surface of the Earth. And if I relate those two equations to one another, we find that the mass of me, or the mass of the small object, drops off. It's on both sides of the equation. And we get an equation for the acceleration due to gravity on Earth's surface, or the surface of anything. So little g equals big G times the mass of the planet divided by the radius of the planet squared. And this is where, if I knew the mass of Earth and the radius of Earth, and plug those in relative to this equation, I would find that the acceleration due to gravity is 9.8 meters per second squared. This is a way of calculating the field strength, the gravitational field strength on a planet, by knowing big G, big M, big R, the mass and radius of a planet. And then also for an object that is orbiting a planet, so maybe an object, something like a satellite or a moon that's nearby a planet, the force of gravity exerted on that object would not be equal to the surface gravity. And so we can't just use the weight of the object. If we were describing the weight of the object on the surface, we couldn't set equal to Newton's law of gravity the weight of that object the way we did in that first example up above. What we could do, though, is we could relate Newton's law of gravitation to the centripetal acceleration, or the circular motion of the object as it orbits the planet. So down below I have a picture of a green planet and a yellow object which maybe represents a satellite that has a mass of lowercase letter m that's moving around in a circle around this planet with a constant speed v. The force of gravity exerted on that object due to the mass of the planet would be equal to g m1 m2 over r squared. And by Newton's second law, that would be equal to the mass of that object times the centripetal acceleration. And so here I've related those two forces to one another, or sorry, not two forces, but the force to the acceleration. And I find that, once again, the mass of the satellite or whatever cancels off. It's on both sides of the equation. And I could solve this equation for the speed. And so I've done that here. The speed squared is equal to g times m divided by r. If you notice, when I multiply this r over to the other side of the equation, one of the r's will cancel, and I'll just have one r on the denominator of the equation. And similar to the beginning of the video where I said an object in uniform circular motion has a straight line velocity, a straight line speed v, goes around in a circle that has a circumference 2 pi r, and does so in an amount of time equal to the period of motion, capital letter T, then I could relate these two equations that I have here. I could relate the equation for the speed that I found with Newton's second law and the gravitation equation to this generic equation for the speed of something moving in a circle. And if I do that, I'd have to square the 2 pi r divided by t, because in the top equation it's v squared, and when I do that I get 4 pi squared times r squared divided by t squared, which is still equal to g times m over r. And so what I've done is, lastly, you might remember a problem that we've done in the past where we solved that equation for the period and found that the period of something moving in a circle is proportional to the cube of the radius of its orbit. And maybe that's even something that's worth remembering, because it takes quite a few steps to get to that point. So maybe just remember that something that's orbiting an object, some satellite or a rocket going around a planet, just remember that the period of its motion is proportional to the cube of the distance from that object to the center of that planet.